Hello, students, at-home students, particularly here before the class comes in. Just want to say hello and happy St. Patrick's Day, as we're going to finish up 2.6 and possibly start on 2.7. Just depends on how much homework questions we have as we go from there. Anyway, so let class begin. Okay, we are continuing with 2.6 rational functions here. So just a quick recap what we've done, put our minds in sort of like math mode here. So finding domain all the time, really quick here from the original problem, it is all the times where our denominator is equal to 0, because you cannot divide by 0. We good? It breaks the graph. So this one, 0. This one, if you said equal to 0, you find -4 to be the problem area. This sometimes you actually do have to do a little bit of work. Sometimes you actually have to factor things down and solve them in order to get the answer there. And sometimes it never does equal 0. So it will just always be a positive number, because if you square anything, the smallest number you can square would be 0 technically, right? To get still 0, but +1, still get a 1. So there's never time this guy equals 0. So all real numbers are great. Camille, question. Yes, absolutely. Turning lights down.
Maddie, I can't see. Don't shake it at me.
Like that or like that?
Oh, whatever.
I like all going out.
All the way out, is good. Tristan and Dylan, do you guys see your sheet of paper? Annette, please see your sheet of paper to write on. Okay, your young eyes over there. Okay, are we good there with that? Domain, original problem, see what the denominator gives you 0. Next, something called vertical asymptotes, horizontal asymptotes. Horizontal asymptote is what happens at the end. We say in behavior, you can cross a horizontal asymptote in the middle, because all it's talking about what's happening at the fringes of things. We're good? All at the ends. Vertical asymptotes you can't touch because it breaks right there. And there's a close connection between vertical asymptotes and domain, but it's not exactly the same. We'll see that today. All right, jam. And then we have this. Vertical asymptotes, pretty easy. For vertical asymptotes, what we always have to do is we have to have no common factors. We get it. So vertical asymptotes have to happen in reduced form after we get rid of all the common factors. Step 2, horizontal asymptotes are determined by the degree of the polynomial. If the degree on top is small degree on the bottom, we call this a proper fraction. Hey, you guys remember proper fractions from elementary school, right? It means the number on top was smaller than the number on the bottom. That means the x-axis is the horizontal asymptote. If they're exactly the same degree, that means you just take the front numbers, the coefficients, leading coefficients, and you divide them, and that becomes it. If the number on top is bigger than the number on the bottom, there is no horizontal asymptote. We good? We call that an improper fraction. Remember that from algebra or from pre-algebra. Cool. Jamming. So we started it with that. We looked at some examples here. Won't go into that because we covered it last time. And then we started finding them. Again, not going to go over that again as we did that before. And so we come to graphing these guys here. So we found out, instead of doing like 7 points, right, like we did in algebra 1, all we'd have to do is we'll just find out y-intercept, x-intercept, vertical asymptotes, horizontal asymptotes, done. Makes it a whole bunch simpler. Hopefully you guys agree. And we did this one. And that little dot sort of confirm which way we go. Again, a little dot, just a single dot, and then we know which way we're going to go. So let's jam to number 5. Can we do this one?
You said x over.
X divided by x squared minus x minus 2 is what we're looking at. All right, if you want to write it a slightly different way. You can write it as just x on top only. This is x squared minus x minus 2 on the bottom here. So before we start doing anything at all here, it's just a lot easier to write things in factored form because sometimes we'll need that here. So this guy written in factored form, does that denominator, does it reduce or does it factor? What do you guys say? Two numbers multiply -2, add to -1. X minus 2 and x plus 1. Are we good there? Everybody agreed? Because sometimes we'll need that factored form anyways, right? So now let's jam. So number one, the y-intercept. What is the y-intercept? And which one is it easier to plug into? The original problem or? Say again. Maybe, yeah, maybe the factor one. This one probably depends, I guess, whichever one you want to do. And this one's easier because all the x's turn to zeros. And so you're left with a little -2 on the bottom as opposed to having to multiply again. So if I turn everything into zeros, I get 0 over -2, which is just 0. That's cool. So we have ourselves a y-intercept. And if you want to, you can actually put it in coordinates even if you like. That helps you. Okay. So then step 2 is the x-intercept. X-intercept reach to the top, the numerator now. Numerator goes like this. And you're saying, when does the numerator give you 0? Oh, it's x equals 0. And you kind of already knew it already because of this little piece right here, right? That's easy enough. Step 3, I need the VA, the vertical asymptotes. Now this comes from your reduced form. All right, that one, reduced form, let's see, when do these guys give you a 0?
Is it for each piece of the bottom of the graph?
Absolutely, yeah, anytime it gives you a 0, Do a -1, perfect, okay. 4 is the horizontal asymptote. And again, those are built upon different conditions, right? So what do you guys say? The degree on top is a 1, right? The degree on the bottom is a 2. It's a proper fraction. So going back over here, this little guy, it is, where are conditions? So sorry, we're gonna go all the way back. Sorry about this here. Go back all the way to here, right? Is it A, B, or C? It's A. The degree on top is a 1. Degree on the bottom is a 2. That's a proper fraction. So we have ourselves a x-axis is the horizontal asymptote. Let's jam up to here. Dun, 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 dun. Sorry, all the little slide rules here. Everybody okay with that? That's cool. I think we're ready for graphing. Based upon that information, let's see. Every once in a while, you'll actually have to put in an extra point in here somewhere. So maybe this is the case here. We'll see. So first things first, I have myself x and y-intercept. They're at the origin. What's some other stuff here? Vertical isotopes. I have them at 1, 2. So there's my vertical isotope. I have the other one is at -1. There's my other vertical asymptote. Boom. Oh, bummer. Shucks, this is one of those. Let me guide you through it here. Let's see. Because of that little 1 dot, I'm still not quite sure how it goes. I have some options. Can I just show you guys the options here? Option 1 is it went like this. and then it went like this, and it went like this. That's option one, because oh, you know what, I should draw in my horizontal isotopes as well. So that's option number one. Option number two, it would have started off low first, then starts from the high to low, and then starts off like this. Oh, so based upon that one little point, this time I can't figure out which way it goes. So all I need one other point. It doesn't matter where it is, as long as it's not at 0, 0. So give me one other point. Which is the easiest one to plug in, you think? Yeah, f of x equals 1. That would be the easiest one to plug in. Once I know that, I know the rest of it here. So can we plug in x is equal to 1? Let's see where it ends up. All right, 1 on top. I'll do the tough part. 1 is on top. One minus what of it? -2. I gave myself a -1/2. Everybody agreed? Agreed with the -1/2. Dun, dun, dun. Awesome. So this guy is right here. Now I know exactly what to do. I know exactly where things happen. Good there? So in order for this to be true, it has to be coming down from the top, hitting those 2 dots, and then going down to the bottom. There's no other way this can happen besides this right here. Now, start picking on people. Is that okay? Love it here. Let's see, starting off. Isabel, how do I know it's not this, but it's this? That's okay. We covered it. I mentioned it last time, just barely. Oh, okay. So I know that to be true because the exponent upon this factor is a 1. It's an odd exponent. If it was a 2, we would be starting at the bottom. So even exponents for your factors, make them go the same direction. Odd exponents for your factor, make them go split direction. Good. So again, just a few little things here. So let me, just for fun of it, if this was a 2, if I just change that to a 2, then I know this would be going this way right here.
And wouldn't they still be going the same direction? Just down together?
Say again?
Or when it goes the other way, they're still going the same direction.
We're talking about at the dollar line. 1 is down, 1 is up.
Yeah, we good? Okay, and if this was, let's do another thing here. If that was a 3, instead of a 2, then we have split direction again. Then we have this one. So it's just a matter of even and odd. We good? Even and odd. Oh. Okay, so let me erase a few things here. Okay. Okay, because it's a 1, it's a split direction. I know this to be true, and then it doesn't touch the x-axis, so it has to turn, and it makes sense as it's going very close to our horizontal asymptote. The other way around here. Okay, that x plus 1, which means this little asymptote here, I get this guy, and that split direction or same direction?
What's wrong with that?
A split direction or same direction at x equals -1?
Oh, same.
Same.
Well, since the 1, you said if it's like even.
Yeah, if it's even, it's going to come together.
Oh, with them. Yeah. Split them.
Split, yep, it's a split direction here. Notice I'm actually graphing backwards, right? Notice I'm actually going like this. Right? You could have done it forward, but I'm just going to give you that split direction. And then done. So real quick here, Camille, does this graph cross our horizontal axes or horizontal asymptote? The other answer. Does it cross our horizontal asymptote? Yes, it does. Absolutely. Right at 0, 0. It crosses a horizontal asymptote, but because horizontal asymptotes are only concerned what happens at the ends. We good? We don't even worry about them until we get to here and here. That's when they become an issue. Okay, cool. Landon, do we cross vertical asymptotes?
No.
No, we cannot cross vertical asymptotes. We good? Have you guys ever heard the MC Hammer song, Can't Touch This? Think of those as vertical asymptotes, okay? Can't touch this. Okay, next one, all yours. Oh, no, not all yours. Let's go with this one's a little more complicated. Let's talk about this one. And it's the next step in this process. Next step in the process. All right, let's do this one together as it's going to get a little bit more complicated here. So first things first, let's write this in factored form. So if you want to write it, just kind of to write it first, this would be x squared minus 9, and this would be x squared minus 2x minus 3. That's cool. All right, in factored form, it would be ooh, okay, x minus 3x plus 1?
Yeah.
Okay, oh, hold on, look at this real quick here. Dun, 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 dun. X minus 3 is a common factor. So we have ourselves a simplification here of just x plus 3 on top, x plus 1 in the bottom. Here's our little problem. We're good? So as we go through this, let's put our thinking caps on. Let's see what happens here. So first things first is our y-intercept again. Y-intercept, a lot easy to go back to the original problem. Because what you do is you just make this a 0, that's a 0, and that's a 0, and you're just left with the numbers in the back. Y-intercept is 3, perfecto. Let's erase that.
You can do that with the factor one too, right?
Which one?
The factor one, because the x is just go away and it's 3 1.
Yeah.
Let me just kind of think here if that's going to be always the case. Yeah, let's check out the next one. We do the slant asymptote. Let's see if that works for that one. So Isabel is saying that if we do this right here, we would get the same answer anyways. Okay, let's see if it works for the next one. Make sure. X-intercept. So the x-intercept, here's our little problem here, and let me think about it here. Yep, let's go with, oh, let me just check something real quickly here. So we go back to the original problem right over here. So x-intercept are original problem pieces right here. And then we have to do the factoring again. With x is equal to -3 and 3. Okay, so let's do this here. If we need to label them here. This will be 0, 3. That's the y-intercept. This would be -3, 0, and 3, 0. Is that true? Okay, and let's think about this here just for a second here. Notice, and here's what we got to get to here. Notice that these two are different, right? Notice that x equals 3 was factored out already, right? Let me go back, sorry, as I'm thinking about this here. Best way to explain it here would be that the fact that because x minus 3 got canceled out, this little guy does not exist. We good? So maybe it's easier actually to use the factored form for our x-intercept. There, the only x-intercept here is x equals -3. And we'll see that when we do the graph. So right over here, use simplified form. Go ahead.
How we get the x-intercepts with the fractions is kind of confusing. So do we not just take the, what makes x 0 on the top of the fraction only?
Yeah, on the numerator, And what I did is I did the original graph. What we should do is we should use the simplified form. And we'll see in a little bit why. So simplified form, you good? Number 3, vertical isotopes. The fun part begins again. We're gonna go and use this little piece right here. It's the simplified form only. And the only vertical isotope we have is at -1. So off to the side, what we should do is do this here. What's happening at that x equals 3? And right next to it, even though the book doesn't mention it, you're just gonna put this whole at x equals 3. Okay, and then the following part here. What happens here?
Why is it just -1 now?
Because we were able to factor this guy out.
Oh, to get the vertical just in the simplified.
Only from simplified version. And x-intercept also only from simplified version. So I should erase this here. My fault here, as I was kind of thinking about it here. We should erase this right here. Let me do that again, just so we got it here. So this would be x minus or plus 3 is equal to 0. X is equal to -3. And we have ourselves -3 comma 0 is your x-intercept. We good? Does that help? Horizontal asymptote, a vertical asymptote, x equals -1. There's a hole at x equals 3. We don't know what the y value is, but we just know the hole is there. And horizontal asymptotes, what do you guys say? Case A, B, or C? They're improper, or so they're proper, they're the same, or they're improper. Same. So in this case, it's going to be the ratio 1/1 or just 1. Okay, I think we're ready for graphing. Let's go for it here. This is usually as complicated as it gets right over here. Okay, got that. And let me switch to a different color so we see the graph a little bit better. At x equals -1, we have ourselves that. Forget the hole for now. We'll deal with the hole in just a little bit here. We may want to just kind of just spot it where the hole would be here. So let's do this here. Go 1, 2, 3, just where we know here is going to have a little problem. Say again, say again.
I thought the y was a -1. Yeah. Sorry. Yeah.
Yeah, it would be this guy here, x plus 1 is equal to 0, and you would solve it for this to get that right here. So it's the denominator. Horizontal asymptotes would be the ratio of your leading coefficients for this one. So I got that. I got, let's see, a 1, 2, 3. I got a dot right over here. I have a dot at -1, -2, -3. I got a dot right there. And I got a horizontal asymptote coming through right over here. Boom, are we good? Okay, based upon that information, can we graph this line? I think so. I think we can graph this line. It has to start off right here, a little bit below, because it has to cross this little guy here. And then it's going to turn and it's going to get close to the vertical isotopes, but not touch. Next, on the other side, it's going to start off high because we have split direction. Everybody agree? Split direction. Dun, da, da, da. And we come down like this, and then kind of careful over here. As you're turning it right over here, let's stop right at x = 3. Stop, dan, hold the phone. And right at x = 3, what we're going to do is we're going to put a little open dot right there. And that's our little hole. It means that for some reason or another, we don't think of 3 being part of the domain that we have. We're good? Yeah. Now, if you graph this on the calculator, your calculator won't show it because what your calculator does is just, it does like 2.8736. It calculates it. The next one, it jumps to like 3.04426. It calculates it and it draws a line between them, right? It doesn't think about this little piece right here. So you won't see it on the calculator. That is it, guys. Was that simple enough? We're good? So we I put these little X's inside here. I put these little arrows here for numbers 2 and 3 because we use a simplified version for those. 1 and 4, we go back to the original for 1 and 4. Okay, almost there, guys. Almost done here. We got to think of one extra little piece right here. So everybody's comfortable with horizontal asymptotes. We know the 3 conditions. There's one little extra little tiny piece here. It's called the slant asymptote. So we've got to do one more, guys. One more. Boom. Slant asymptote is a line that sometimes called oblique asymptote. So horizontal lines come straight across, right? A slant asymptote, what it does, it's a diagonal line. It's a line that goes kind of size, just like our lines that we used to do in algebra. So we have the vertical isotopes, that's great. We have the slant asymptote, and it does this right here. So this would have had no x-intercepts whatsoever. This one would have had 2 x-intercepts right here. It would have went ding, ding, and then come back up. So notice it rolls really, really close to it. Okay, so question is this. When do we have an oblique asymptote or slant asymptote? Good? Here's our little condition. When the numerator is exactly 1 more than the degree of the denominator. So if it's a 4 on top and you got a 3 on the bottom, that's the way I got the case. If it's a 6 on top and a 5 on the bottom, that is the case again. The exponent, the degree of the polynomials. Okay, are we good there? Isabel?
Is the slant always going to be the exact same?
No, we're gonna have to find the slant there. So let's do this here. For this one, let's find this little line right here. It actually even gives us, it says y is equal to x minus 2. So question is, how do we get that? Oh boy, you know how we get that? We get that by long division. Remember this little guy from a while back? X squared minus x plus 0. Remember that little guy? Ouch. Okay, let's go with it real quick here. So you guys talk to me. X times what gives you x squared? X, put it inside the x column. X times x is x squared. X times 1 is 1x. And we subtract. Or even better yet, we. Good, I heard it. Yeah, add the opposite. So plus, make that into a minus, make that into a minus. Let's add down, and that better cancel. Negative x plus negative x.
Oh, no, sorry.
Negative 2x. And then we bring down the 0, and we start the process all over again. X times what gives you negative 2x? Negative 2 here. Negative 2 times x is negative 2x. Better be, because that's what we wanted. Negative 2 times 1. And then what we do is we add the opposite. Oh, sorry, subtract or add the opposite. Let me change plus here, plus there, plus there. That's cool. That better cancel. Oh, we're left with the remainder. That's okay. That's no problem. So here's what we got. We have x minus 2 plus 2 over x plus 1. Are we good? Here's the thing. We don't care about the remainder. Who cares about the remainder here? Our slant asymptote comes from just the quotient, just this little piece right here. And what it's really saying is this: as the numbers get bigger and bigger and bigger, as this number gets bigger, let's say this is like a 100 or so, right? This whole piece, this whole number, pretty big or pretty small? It's small, right? It's 2 over 101, right? So it doesn't really affect this whole equation. Like if that's 100 there, and that's 100 there, this affects our equation. That is not affecting our equation whatsoever. Good? Okay, let's try one real quick here. Boom. So sketch the graph, and I bet you it's going to have a slant asymptote. All right, so let's do what we normally do. In fact, I'm going to write it over here just as a quotient here. So this is x squared minus x minus 2, x minus 1. All right, so in factored form, just in case it's going to reduce, can you guys factor the top for me? Okay, x minus 2, x plus 1. Oh, awesome, that's cool. Okay, so I got that. Nothing cancels, right? That's cool. So no holes here. So that's cool. So let's go with it here. So bam, number 1, y-intercept. So 0, 0, 0, 0, that all goes away. Two. So right over here, how about a 0, comma 2? X-intercept. Right, reduced form if we have it, right? Reduced form if we have it, we don't. So then these are a lot simpler to work with anyways here. If I have that to be true, then I know this to be true, this to be true, therefore 2, 0, negative 1, 0. Are my coordinates. Number 3, vertical asymptote still comes from my reduced form, VA. X equals 1, okay, boom. And then 4, it goes back to the original in your horizontal isotopes. Yeah, for horizontal isotope, there's no horizontal isotope. There's nothing that comes across, right? This is none. Right, so horizontal isotope, there's none, but then we have SA, slant isotope. Oh,
Is the none because of the ratio of the exponents? Is that how it works?
there's none because of that exponent and that exponent. It's improper for our degrees, we good? But then we say, oh shucks, it's improper by only 1, because we have 1 degree in the bottom, but we have 2 degrees on top. So therefore, we have ourselves a SA. Anybody want to write an essay? Raise your hand if you like, you really enjoy writing essays. Depends, okay, depends on, okay, gotcha. All right, this one, a different essay to write. We just go like this, x minus 1, x squared minus x minus 2. We have to find out the quotient. Dylan? Say again, no, sorry again.
How come there's no horizontal axis?
Ah, gotcha. Dylan's asking, how come there's no horizontal asymptote? Because our conditions for a horizontal asymptote is if n is less than m, so the degree on top is less than the degree on the bottom, my horizontal asymptote is y equals 0.
Oh, you take that from the original equation, not the reduced one,
Yeah, correct. Our original equation right over here.
but then for the other one. you take the reduced
Just for number 2 and number 3. That's why I make these little lines. The lines say that I'm going to take it from the other two. If they're the same, if they're exactly the same, that means it's the ratio of your leading coefficients. But C says if n is greater than m, then there's none. Good there? And then there's almost like this little caveat right here. It says, hey, you know what? If m plus 1 is equal to n, if it's a difference of 1, take the bottom one, add 1 to it, then we have an SA. Dylan, does that make sense there? So C kind of gets an extra little filler right over here.
one. What does SA stand for?
Slant asymptote. Slant asymptote. All right, let's jam. So we have to get it into long division again. And here we go. We're just trying to figure out what's on top. So x times what gives you x squared? X, and of course I'm gonna start picking on people here. So x times x is x squared. X times -1 is -1, negative x. Is that right, negative x?
Yeah.
I think so, okay. That's slick. Okay, subtract or add the opposite here. So I'm gonna add this, add the opposite here, add the opposite here. That better cancel. Hey, that's cool, that cancels. That cancels as well. So I'm left with this right here. Okay, so technically that -2 is already the remainder. We good? Because there's no way I can multiply x to give me a -2 without the x not being there. We good? So that x is here. Then you have the remainder of -2 over x minus 1. But do we care about the remainder? Our slant asymptote, write it down here. Y is equal to x is our slant asymptote. And Dylan question.
So will there always be a slant asymptote if there's no horizontal asymptote?
Good. Question is, will there always be a slant asymptote if there is no horizontal asymptote? And the answer is no.
So then what determines that there is this slant asymptote?
Perfect.
I think he
Perfect
said,
question.
so if it meets condition C, right? If the exponent of the bottom one, if you just add 1 to it and it's the same as the top one, is when you get a slant asymptote, right?
Perfect, yeah.
Yeah.
So Dylan, only if there's a difference of this and this by 1.
You take the top exponent, you subtract the bottom exponent, you get 1, then you have a slant asymptote.
And then anything else, it should be none and none. Yeah, this comes off of this condition, I guess, yeah. Okay, so I think we are ready. Are we ready? Can you guys try it yourself first? Go for it. You're gonna have to draw in, this is a dashed line, just like we did the horizontal ones. And really, the difference between horizontal asymptotes and slant asymptotes is the slant is a diagonal, right? The horizontal has to be a horizontal. It has to come across, straight across. So I'm going to erase this as we go. Let me erase that. I'm going to just duplicate the slide instead here. Hold on. And we found out that to be true. There, just so I have it as a reference here. Okay, I'm gonna erase this guy. Oh, interesting. Never mind. Can't erase it now, huh? Well, that didn't work the way I thought it was gonna work. Okay. Better than like this. Okay, so let me graph this guy. I'm gonna have to go back and forth between this here. 2, 0. There's my 2, 0. 2, 0, negative 1, 0, 2, sorry. 2, 0, negative 1. Okay, everybody good there as far as dots are concerned. Do we have any vertical asymptotes? And vertical asymptotes, so I don't have to go back and forth.
Isn't the vertical, this is the same one? Yeah, this is the vertical asymptote one.
Yeah, I'm just, so I don't have to go back and forth between graphs themselves. Did I get all the y-intercepts? Did I get all the x-intercepts? Okay. All right, and the fun part, not a horizontal asymptote, it's a slant asymptote, it's y equals x.
No, it's the perfect slant.
It is perfect, yeah, it's this little guy right here. Of course I would make.
Not like I get like If it was like a normal linear function.
Yeah, good. Question is, if it was a normal linear function, like say x minus 2, right? Then yeah, you would have to go like this. You have to plug in this little guy here and maybe make a slant out of it. And then go. Say again? Yeah, I would do a slant instead of a dot because the dot's going to confuse everybody. So if you're going to do like this, let's say this was a slant asymptote, you do a slant here, then just keep on going. That'd probably be the easiest way to do it. Just so you're not confusing with the dots. Okay. I think we're good. Okay, now the question is this. Does everything make sense? And so we have one of two options. You guys ready? Option number one, of course, I'm going to give you the bad one, is this one right here. The graph is below our slant asymptote, and it would go something like this. True? No.
No.
There should have been an x or y intercept right here then, right? That's not true. All right, that means it's on the other side of the slant asymptote, and it goes like this, hits here, and keeps on going right there. That makes a lot more sense. Flip to the other side. Oh, split direction or same direction, Charlie? How come? Almost there, yeah. Go ahead, go ahead. Sure, yeah. Let me say it here. So because the factor in our denominator, right, has an odd exponent. Very good. So it's always about the denominator. The denominator has an odd exponent for the factor. Okay, boom. If that's the case, it has to start down here. There's no other place it could start. And then it nicely goes through this. Do we have any holes or no? No, no holes. Okay, that's cool. So then voila, that is so awesome right there. That is it. There's our graph. And we have finally, almost in a sense, come to the end of these rational graphs here. So you guys should be able to do them really quick now instead of algebra 1.
If the points were different and the graph on like the other side of the plant, would it just be like the V kind of?
Yeah, like the.
This one, it would have had an x-intercept, right, a y-intercept here. It would have to have that right here, right? And then the other side would have had nothing yet. Then it comes down like this. And it would have came right back up.
And is there ever a point where you have all four?
Question is,
It would be past that.
you would never have all four because they're
There's
not
no
big.
way to hit all four of them without doing that.
Okay,
You have multiple values for y for x, and it's not
Down
one.
if it crosses 2
Mhm,
points. That's
correct.
my function.
very true, very true.
I
Okay.
will watch you, you'll fail.
Oh, let's see, you got 4 minutes left. Let's try it here. So where's this stuff used at? It's used at to look at something that can't happen. That's kind of what we use rational functions for, or we call it a limit. And so this one's a pretty good one here. It says the utility company burns coal to generate electricity here. And so now the question is, it goes from 0 to 100 for the p value. This is percent. Let's see. Oh, removing p% of the smokestack pollutants here. So this is right here. And so think maybe the best way to think about it is, let's say you are picking up garbage off of from a river or something, right? It's a food, right? So the big ones are the easy ones to pick up, right? If there's a Coke bottle there, you just pick it up. You've cleaned up some of it, right? And so now the question is, well, what happens if there was a little bit of maybe like a chemical inside the water itself? Well, that will become, you can't do it just by picking up with your hand, right? That means you need maybe like a filter or something, right? So now you have something else that needs to happen in order to clean up that piece, right? So then filters become microfilters if you need very, very really, it just becomes more expensive, right? To build a microfilter as opposed to a filter, as opposed to just picking up the Coke bottle with your hand. We good? And that's kind of what this is. It's, even though it does a good job, even water filter at home, right? I read the little tags on it. It's clear as 99.99% of all things in your water. So it does a good job for $300. That's pretty good. So this one, if we were to sketch this here, so P is the number of percent here, and we only have just a few minutes left here. So if I were to plug in 90 into here, so 90 comes into here, that's a big number. And then 90 comes into here. So what's that? 720,000 over 10. So in order for the utility company to start removing 90% of the waste, it'll cost $72,000. Are we good? 1, 2, 3, 4, 5. 1, 2, 3. Yes, thank you so much. 2 zeros here, added there, and then we have an extra one. That good?
720,000.
At least cost-wise, yeah. And again, we have to figure out how much does it take to produce the filter, how much does it take to clean the filter or replace the filters as needed here. Just a quick example here. I know we got less than a minute left here. So notice that, can you ever get to 100? Is there a time that you can get to total 100%, no is a pollutant whatsoever? No, because of just the model itself here. You can't plug in the 100 into that little piece there. And so let's see how this works. If you're to graph it, it sort of looks like this here. For the 85%, it's somewhere over here. For the 90%, it's somewhere over here. So then the question is, what is most cost effective to get rid of the most while still being able to function as well? So that's kind of what this one is all about. Okay, and with that, we are out of time for the day.
Now, we are the 2.6
Yes, 2.6 homework, please start on it. We will take the time on Friday to go over any questions you guys have on it, and then it'll be due Friday evening of that day. And with that, have a great day.